There's no forces outside the system.
What would be like a force outside?
I'll show you.
Like a hand.
So we're going to take this framework here. Okay, we have a car moving, and it's going to hit a car stationary. All right. Now, after, something is going to happen here. I'll draw it over. The original car is more massive. Okay, the original car is more massive. So when it hits, what's it going to do? Is it going to come to a stop, move backward, or keep going forward?
Keep going forward.
Right?
Slow.
If it's more massive, then it has more resistance to change in motion. It's going to keep going. But what's going to happen to it?
Could be parts.
Yeah.
It's going to slow down, right? If it slows down, what happened to its momentum?
Decreased.
It decreased.
Transferred to
Yeah, it's like where'd it go?
the other car. Shift velocity.
So, oh, is this the elastic and inelastic?
Oh my gosh!
What
Oh.
a transition.
What,
you
you
said
just
it's
hit a
off
home run?
Did Dexter hit a home run?
No, his.
Oh.
Say Suzuki hit 2 home runs today. Yeah.
So I think you guys are right.
You're just gonna leave
His,
it like that?
his,
He's
No,
the Cubs
it is.
rookie.
There's video and
Japan.
it's not gonna say.
Oh, I think we should.
So this car slows down, some of its momentum is transferred. Now, let's take each car individually and let's see what happened. Okay? So what happened to the red car?
oh, which one's right?
What happened to the red car? If we just look at the red car, did it slow down?
Yes.
Absolutely. Did it lose momentum?
Yes.
So his momentum is not conserved.
Well, each individual car's not, but as a system.
Okay, so this is what we're talking about.
So you have.
What about
to-
the blue car?
Oh.
It was at rest,
So gain.
and now it's moving, all of a sudden like, whoa, momentum!
So that's why we use like ND plus ND.
So what we need to consider though, is we need to consider them as a system, because if you consider them as a system, okay, we can talk about the conservation of energy. So why did the red car slow down? Because when it collided with the blue car actually pushed it backward. True?
Yeah.
If the red car is just my system, something outside the system pushing on it changed its momentum. Same thing with the blue car. If I consider just the blue car my system, the red car crashes into it, the red car is outside the system, it pushed it, it changed its momentum. Okay, yeah.
So could you just keep going, like, keep expanding your system if you,
Yes.
So that's
Hold
why
on.
it's conserved in the universe?
Yeah, yes, the total amount of momentum in the universe stays the same.
Because it's the same system.
So if we consider both cars our system, do they collide here? They do, right? But that's a Newton's third law force pair that is within the system. And as long as there's no forces that are outside the system, then momentum is conserved. Yeah.
What about like, energy initial is always equal to energy final, right?
Not always, but
What did you just
in
say?
general.
Energy emissions. I don't know exactly.
Oh.
In our scope it is,
So
so with the
it-
red car, where's
If there's friction.
So not here, this is a collision. Energy is not going to be necessarily
energy
conserved.
is the
If there's a
inelastic
spring.
and elastic.
It's like if it's the.
Momentum's the
bouncy
one that's
unit.
always converted.
Yeah, momentum is always conserved for us as long as there's no forces outside the system.
But we can expand the system to keep making it, yada, yada.
So why isn't
But
energy
we don't
conserved
have
like
to,
in this
that's
collision
it.
though? Like could you?
Well,
get,
it may or may not be, it depends on the type of collision. So,
we'll
in,
get like one where it isn't conserved.
so
Is that
when
correct?
two objects actually physically hit one another, this collision generates some thermal energy due to the colliding, and like also releases some sound energy and some vibrational energy. So in a collision like this, you're going to get some energy released to the surroundings via those methodologies.
So,
So-
sorry.
Go ahead.
I was just gonna ask, so is there like a little thermal energy that's released if the car is going like super slow and like barely?
Well, so maybe, maybe not. So one of the things that we don't consider here is any friction with the surface.
Right.
Because if there's friction with the surface, you would actually transfer momentum into the surface via vibration. Okay? It really depends on what happens at the collision site here. If there is a spring and all the energy can get stored and then released again, then you can have an elastic collision where both momentum and energy are conserved. Or if this were magnets, you guys know how those, like, those cars back there are magnetic? That's a cool thing because you can store energy in the magnetic field and then get that energy back out again. So those could be elastic collisions
Wait, how does
also.
that work? What do you mean by that? Like, the spring pushes back upon it, the magnets hold it there.
No. If you put north via north,
Oh, like, okay,
right?
I was thinking of stick.
Not north and south. Yeah.
So Sam was saying, like, if you're in a room, like, the total momentum in the room is constant? Is that true?
Unless someone walks in the room.
Well, right, if no one leaves the room.
But like,
Yeah, I suppose. I mean,
What if everyone just, like, sits down? Like, it's still,
well, so here's the thing though. Like, if you're interacting with the ground, right? If you're interacting with the ground is probably not part of your system. Let's talk about it in a different way. Let's say you are astronauts floating around the International Space Station.
We made it.
Right.
close.
As long as you don't touch the walls, whatever happened in interactions between you guys, you would just exchange momentum between you all, right?
Oh,
Some
yeah.
people could speed up, some people could slow down.
but whatever it was is what it is.
Exactly, unless you touch the wall and the floor.
Oh, because,
And then
but
you push
can't
off the wall
move
and the
in
floor,
the
and then
International
it
Space
adds
Station without
momentum.
That's right, if you push off the
applying
wall,
force to you.
Oh, it reminds me
Yeah,
of the
it's
thing
like
where we're
when they're
spinning.
actually
I'm giving you my
push off
momentum.
to the side,
So we push in the
it's
opposite
slowing
direction.
down space
Or,
station,
like,
just like
when we
under
twist this way,
control.
our little arm twists the other way. It's,
there's
that.
nothing outside the
But
system.
when you
Yeah,
push on the
And that's
wall,
what
kinda
actions in the
puts
space
it-
station are for.
That's what makes it.
but you're not creating momentum, so
They
is it just
create
like,
thermal
it comes
energy.
from the wall?
They're
or-
swimming in the.
Like when you push on
Oh my
it?
god.
Yeah, it's an outside
yeah.
force.
Okay.
That's how
Yeah.
a car, if you look at a car in a system, it creates thermal energy into
Yeah.
connection.
All right, now, there's one more thing on here that I want to point out, and it comes right after A is equal to F net over M.
It's the coming.
What?
It's coming pretty slowly, what are we doing here?
I
Is this
think
the,
I
is
think
this
it's the
the,
floor cleaner.
is this the floor cleaner?
Oh, I thought it was.
Is this guy in a Zamboni?
I want to see him come high.
Oh, yeah, one of these.
Let's hope that we can get this whole school done. in 10 minutes.
Wait, that's what I'm
No,
trying to
Greg needs to hop on.
Let's go out and cheer
How
on.
does that?
Wait, it comes right after abortion.
Yeah, it's like the fourth one down or something. All right,
Oh,
The
So-
floors look exactly the same.
if you look at this, okay, if you look at this, it says the force, now I wrote net force and that's fine. This is my favorite equation of all time, because it's dp dt. Just throw that out there.
Oh my goodness.
This actually is what Newton said. We attribute F equals ma to Newton, but that's not actually what he said. Newton said that if you have an unbalanced force, what it actually does is it changes the momentum of your object.
But then if you look at that in 3-dimensional or linear,
I mean, if you expand this out,
um,
this is the change in momentum, right? So this is actually
mv squared.
d of mv
Oh, I get it.
over dt, right? And if the mass of your object doesn't change, then you have m dv dt. And if you've been paying attention, you know dv dt is the acceleration.
that's sweet.
Isn't that cool?
Yeah.
Oh,
I understand. I'm just
my
like
gosh.
elaborate.
So as long as mass.
Purple
is constant.
diarrhea.
Sure.
Yeah. Which
Now-
normally.
The derivative of
Uh.
v over t is, I thought v over t is acceleration.
It is, but that supposes that you start from 0 on both of these things. So our general concept for
Oh.
acceleration is the change in velocity divided by the time, okay? But that gives you an average acceleration, because I don't actually know how your velocity is changing. Your instantaneous acceleration, right, if you want to know what your instantaneous acceleration is right now, you need to actually take the derivative of the velocity equation with respect to time. That'll give you either the instantaneous acceleration or an equation for acceleration, okay? But this is our, just the general idea. Acceleration is a change in velocity over a change in time, okay? Now, occasionally,
Oh,
am I Bob?
oh, we broke through the
I like it.
fourth.
Occasionally, you could have a problem where the mass was changing, which would be super annoying, okay? I haven't seen one in a
Like
very
a-
long
like
time.
a snowball or
Mass.
something.
Yeah, right, snowball rolling down, right?
Oh, that's actually really, yeah, that's a really good example. I was thinking, I
Yeah.
was like, how did that happen?
more like there was a problem like, here's a truck. Okay, and this truck is driving this way, and there's sand falling into the truck from like
From the sand compactor.
right, looks like and the sand is falling into the truck.
As the truck moves.
Yeah, so the truck is just coasting by. What's gonna happen to the speed of the truck?
Electrical sand.
It's gonna slow down.
Sand.
Why does it slow down though?
Because there's more
Physics.
gas.
Did you say physics?
Well,
Because physics,
This is
man.
Sod's eighth rule, I think.
Well-
I represent side here.
If we take the sand and the car to be our system, right? The total amount of momentum has to be constant, so PI is equal to PF. Initially, it was the mass of the cart times the cart's speed, but what's happening now?
Mass change.
So I'm gaining this, so what has to happen to my speed? It's gotta be decreasing over time, right?
Oh, so it's like with a sticky collision.
Kind of, actually. I think that's actually a decent way to think about it. Think about it this way, though. This sand hits the bed of the truck, true? The truck actually has to exert a forward force on the sand to get it to start moving.
Oh, yeah.
But if the bed of the truck exerts a forward force on the sand, what does the sand do?
Moves back.
Exerts a backward force, which
Slows it.
slows it down. Right?
That's cool.
Wait, can you explain that one more time?
Yeah. So if you were skating by, right? If you're skating by on a skateboard, and I throw you a medicine ball,
Oh, that.
I would just go,
Yeah.
let's say you can
It's a
catch
broken
it. Are you
column.
going to slow down?
Yes.
You are, because you actually had to apply a force on the ball to get it to speed up with you. But if you're applying a forward force on the ball's applying a backward force on you, causing you to slow down. Yeah, so it is like a sticky collision. It's like the one where the guy swung down and picked up the sandbag, right? He picks up the sandbag, he slows down because he has to apply a forward force on the sandbag, but it applies a backward force on him. So anyway, so this one here, force equal to dP dt. I don't know when it ever manifests. I just think it's interesting. Yeah, let's take a quick break. Brain break.
The arc
I think it might be
I don't know.